I wonder, is it better now? Okay, can you hear me now? Can you hear me now? Can you hear me now? Well, there is a lag, so I don't know where you can hear me now, but at least OBS says that uh, it is going. So, okay, I assume, well, let me just double check that I'm speaking through the right microphone here. Which I think I now do. Okay, and just double check that the stuff here is all right. Okay, yeah. So let me try this again. Welcome to Middle, a show where we try to understand how to build a modern distributed database for financial accounting using slightly unusual coding techniques, like using this Zig programming language, not allocating memory after startup, doing all input-output through IO ring, and assuming that persistent memory, that like non-volatile memory, that disk are actually garbage, and from time to time return you a soup of bytes instead of the data which you originally route into it. Like surprisingly, even in these hostile environments, you can write the database. So what are we up to in these episodes? Well, the same thing we've been doing for the past 3 or 4, where we are looking at how compaction works. So as a reminder, the core data structure of Trigeminal is an LSM tree. Logically, LSM tree is just a sorted array of values. Physically, LSM tree is a bunch of tables where tables are arranged in levels. Each table itself is a sorted array of values. And within a single level, all tables are disjoint. So, like there's like the first table in the level, then the second table in the level, and then the third table in the level, and you know that all the keys in the second table are less than all the keys in the third table. So within a level, you could binary search. That across levels, you don't have this constraint. Across levels, tables might intersect. And the semantics here is that key value pairs from earlier levels win. So if you have, like, if you're looking for a key foo, and you have entry key entry foo equals bar in level 2, and also an entry foo equals quacks at level 4, you return the answer foo equals bar for level 2 because that is the earlier level. And then there is compaction process, which takes a table on one level, all tables that intersect this table on next level, reads all the data from all these tables in memory, then merges the data and writes the resulting tables to the second level. And this process is called compaction because due to this shadowing effect, when we merge values from the top table and the bottom tables, it might be the case that we could just drop some of the values of the bottom tables. Okay, so that is what we are looking at. Traditionally, compaction process is implemented as a background process or background thread. So periodically, some process which is unrelated to the database checks what we have on disk and tries to merge some stuff. For Trigeminal, this background compaction process doesn't work because, as I've said at the beginning, Trigeminal assumes that disk might fail. And that means that Trigeminal replicas need to be able to repair their hard drives. So if one disk block is damaged on replica A needs to be able to ask replica B to get this same block. But for that to work, the replica B actually must have the identical block on its hard drive. So unlike other distributed database, it is not enough for us to guarantee that the data is logically replicated across replicas. We must guarantee that physically the data is the same. So that means that we need to make our compaction process deterministic. We must ensure that if replica A and replica B run compaction process, they end up with exact same data file on disk, irrespective of any scheduling decisions of operating system. The way this works is that we interleave compaction process with normal transaction processing. So every time you process a single transaction, you also do a little bit of compaction, specifically just enough compaction to be able to process the next request which comes into your database. And the full loop, where you do like one whole round of transactions, is 32 requests. So every 32 requests, you do one full round of compaction. And on every request, then you do 1/32 part of the entire compaction process. Okay, so what do we do through these 32 bars? Well, the goal is to do as little as possible. During these 32 bars, we accumulate some amount of changes in memory. So at the end, we need to drop these changes from memory to the level 0 on disk. That means that we need to free space in level 0 for exactly one new table, the data which we have accumulated in memory for the previous 32 requests. This get-in space for just one table in level 0 is exactly what is the round of compaction is doing. And here we're like thinking backwards. So we need to get one extra, we need to have space for one table in level 0. That means that we need to, in case level 0 is already full, we need to push table from level 0 to level 1. But that means that we need to have a free table on level 1, so we need to potentially, if level 1 is also full, we need to push one table from level 1 to level 2, and all the way up to the last level. And I think we have 7 levels in our LSM3 level disk. Each level is exponentially larger, I think 64 times larger than the previous level. Larger in terms of number of tables. So the first level has one table, maximum. The second, the in-memory level, like the -1 level, has one table. The 0th level, the first level, which is on disk, has 64 tables. The level after that has like 64 times 64, or maybe the growth factor is 60. Well, actually, let me just double check this. Double check this, and let's go to the streaming mode. This is constants, LSM growth factor, which is a content parameter, which is 8. Okay, so as you see, I'm not as good at Trigeminal as I'm trying to present. Okay, so to drive this process, what we do is that we divide our bar of 32 requests in two halves. During the first half, we move one table from level 1 to level 2, one table from level 2 from level 3 to level 4, and one table from level 5 to level 6. And we do this in parallel because, well, these levels are disjoint. Then in the second half, we go and move one level from level 0 to level 2, one table from level 2 to level 3, etc., etc. So first we do odd levels, then we do even levels. As a result, we exactly at the end of our bar has this free space in level 0 for a memory table. So that is the overall process. We already looked at the code for selecting which specific table are we going. Well, first of all, we looked at the code which schedules like this: first half bar, second half bar. Then we looked at the code which selects which table should we sync when we are compacting? Because, well, like I say, we need to sync one table from level 1 to level 2, but which table? Well, there is a code which we looked at which does this. Finally, last time, we looked at the actual process of compaction, which needs to read a bunch of tables, merge them, and write the results. And the insight there is that these iterations, reading data, then merging data, then writing data out, can be pipelined. So you first read a little bit of data, and then you start merging this data. And while you are merging this, you could continue reading more data. And then after you merge something, you start writing to disk. By that time, you read a little bit more data, so you continue merging things in parallel to writing this out, and in parallel to that, you continue to read slightly forward. So this is the compaction pipeline. We run a bunch of compactions in parallel, and each single compaction itself is pipeline. Each compaction is concurrent process. And last time, we stopped exactly where the actual process of compaction starts. So I think it was in compaction pipeline, yeah, right here. And we looked at like this start, where we divide the budget of blocks across compactions. And this bit I kind of like don't understand. So I understand that we have a certain pool of blocks which we use for compaction, and this blocks goes from like this block pool, but I don't quite understand yet like how exactly we like budget those blocks, how exactly we allocate them, how exactly we are freeing them. So this is what we are going to figure out today, hopefully. Okay, so let's start looking into how the actual compaction process works. So kind of like as a reminder, kind of like this advanced pipeline is the overall loop which juggles this concurrent read, merge, write process. And on every call of advanced pipeline, we like try to kick off some of the work. Like we try to kick a read or a write or a merge. And this starts with kicking up a read. So let's see what this bleep read function does. The bleep here is, I think, this single turn of advanced pipeline async loop. Okay, so we need to go and read some data. Already we see here that we either are reading the index blocks, or we are reading the data blocks, or as we are starting to call them, values block. As a reminder, like our tables are two levels. So there is index block, which stores pointers to the data blocks, and the data blocks store the actual values. So in our bit, we store this index read done, which says, hey, what should we do? So apparently index read done is, well, before we go ahead, let's see this like activated and assert. It's kind of like, does it do anything? Well, yeah, it doesn't. Doesn't really do anything useful. It just sets up the callback, and actually, well, yeah, and that's it. So we start in a situation where index read is not done, so we go and read the index block. Now, okay. The question I'm wondering here is like, which index block are we going to read? Because, well, obviously we need to read a block from one input table on level A, but there is like, a bunch of tables on level B. Like which table on level B are we going to read? Well, let's read. Like I kind of like guess what we that the invariant this function tries to enforce is that we have index block for table A and like the current table B in memory. Well, let's see. Okay, so if what we are merging is immutable table, so the table which is in memory, then obviously like all the values are in memory and we don't have to merge anything. Okay, so that's simple. Otherwise, we are merging something from disk. So we have this compaction blocks thing, which hopefully I will understand at some point. So, okay, we say that. Okay, so, I guess the first thing here is like at this point we actually already have these blocks set up, and that is done by assign by bit blocks assign. Yeah, so well, blocks is blocks is the bit thing, and we assign the blocks here, and the blocks is what we get from okay, I think it was happening in the forest. Yeah, this is, yeah, so kind of like the compaction, like each compaction is specific to the tree, but the resources, the compaction is using the blocks belong to the forest level. So divide block takes some blocks from forest level and gives them to the compaction. Okay. So anyway, kind of like we have these blocks and we set the target. I think this is like setting the target is for the callback. So yeah, okay. This actually feels simple. Yeah. So we have this block which is a slice of bytes in memory plus an input-output operation for read. And we say, hey, read, please read this block using this read structure, using this address and this checksum. Like again, as usual, the question is like, how do we know like the address and the checksum? Well, and the answer is that this is the table A. So this is the table which we chose to compact. And we had run an algorithm which looked at all the tables on level A and select the one which we want to compact. So yeah, that's why we already have this address in the checksum. And okay, kind of like when that's going to be done, bleep read index callback will be called. Okay, seems is enough. Now, what I was interested in, like which level B table are we going to read here? Okay. So we have source B position, kind of like which table from the level B we are going to read, and we get this table, and we go and we read this table and we advance. Well, we don't advance this index, we advance something else. Okay. Oh yeah, and we increment like this amount of like pendant read operation. So I think we should assert that pendant index is less than or equal to 2. I think because this isn't actually a loop, which is a little bit surprising, but well, okay. So if we actually don't have to read anything, then we immediately call this read data, which is exactly like the same thing which happens here. Okay, but let's see what happens once we read those index blocks. So we will invoke this callback twice, one for the block from level A and once for the block from level B. Let's see. So yeah, we kind of like said that, hey, we have one fewer read. Then we copy the data out from the block which was read to us by the grid. And like the reason why we need to copy the data out here is that this block is in a grid cache and it might actually get evicted soon. So I think ideally we should have maybe just a reference counted blocks, or like maybe we need to have some other way to like, you know, just like pin this block and say, hey, please don't free this block out. But like for now, we do this memory copy, which again shouldn't really be necessary. So this is like the design bug. Like, there shouldn't be any extra mem copying happening while we read stuff. Okay, so once we read all of them, we go, okay, let's then read the data blocks. Okay, that should be relatively simple, I guess. So again, I guess here we need to read both the code for read both the values from level A and both the values from level B. Okay. Where do we increment this index block? It's kind of like funny that we haven't seen this incremented yet. Okay, so yes, we do this in update position A and we do this in update position B. So that means that we need to figure out where we call update date position A, and we call that in the bleep merge. Okay, yeah, so I guess kind of like we do index block read, then we do data block read, then we do merge, and only by the time we get to merge, we actually go and update our indexes. Which makes sense, because like, you know, we merged something from table from level A and we merged from level B, but we actually don't know from which side we are going to pull more of the values. Maybe, like, you know, maybe we end up just slurping all the values from table from level A and we need to read the next data block from level A. Or maybe we need do the opposite and actually table A stays put and we need to fetch the new block from level B. Or maybe, like, you know, we consume those blocks simultaneously and we actually need to fetch both of them in memory. So okay, it makes sense that it is updated in the merge. Okay, so anyway, if we are or if we need to read data block from table A, then we source value blocks. Okay, so okay. So it seems like this code is actually trying to be smart, perhaps, and like try to, like, you know, read ahead. So, like, you know, like you're running compaction pipeline. So you like read, merge, write. But how many blocks are you going to read ahead? Like obviously you need to read at least one block, but actually you might want to go and read like a bunch of blocks ahead. So like this block 50 is probably like the least of blocks which we have read. And here we access 0 because this is level A. So for level B, for level B, this is going to be 1. And this is kind of like not really pretty, but okay. Okay, so which block are we going to read? Which is, I guess our like logical position plus the number of blocks which we have already read. And for some reason, this is a var, so we are going to mutate this I. Okay, well, yeah, I guess we're going to read a bunch of blocks in parallel here. Okay, well, let's see. Okay, so index block, by this time we already have, because this is a callback we invoke after we have read index block. So we go to our index block and figure out the address and the checksum of a value block we need to read. And now, okay, so I'll like how many of the blocks we are going to read. So like obviously we shouldn't overread the table. And then we say, okay, so we kind of like, we allow ourselves to read at most half of the blocks in one go. Okay, and then we go and we like just queue up reading of all those blocks and schedule for bleep data callback to be invoked afterwards, which makes sense. So okay, basically we have read index block from the single table from level A, then we read the index block from the first table from level B, then we read a bunch of data blocks, like maybe one, maybe two, like whatever, like, but definitely more than one. Then we do the same for level B, which is like copy-pasted code, which is probably identical, but this comment is different. Okay, yeah, I really hate it when the code is almost the same. But well, okay, it kind of like feels actually the behavior is identical. So okay, basically we kind of like read a bunch of blocks from table A and from table B. Then we call this callback. And what happens here is, I guess, oh yeah, right, as usual. So kind of like standard pattern. What happens here is like, essentially like fan out concurrency. So, and this is really like, nice fine-grained concurrency for which you kind of like really want to have something like async await rather than like Go-style Go routines. Because you don't really want to have like 5 parallel processes here. You really just want to say, hey, I want to run these 5 syscalls in parallel. So it kind of like do very, very fine-grained concurrency. So this is like this fan out pattern. We spawn a bunch of concurrent work in parallel, and to do this we just keep a counter of like how many pieces of work are in flight. And once this counter reaches 0, we will say, okay, so this work is done, like we joined everything, and let's proceed to the next stage. Okay, so when we read the block, again, we do this like architecturally questionable memory copy. And when we've done this, we've done this, we go and push the blocks from pending to ready. Okay, and this is block 5.0. Okay, and here I must say I don't understand a thing. Okay, source variable blocks is 2 5.0s, one for level A, one for level B. 5.0 is just a queue of blocks. When we read a block, okay, yeah, so we call this free to pending. Oh, right. So like initially, like all blocks are in this like free queue. So we pick some arbitrary free block and we say, okay, so this block is now IO in, and once the IO is done, we say that, okay, so now all those blocks are actually in this ready queue. Okay, now it sort of makes sense. So like compaction has this like block 5.0, which is like set of blocks compaction works with, and like originally all the blocks are in 3, so kind of it's just a spare pool of blocks which compaction can use. Then compaction schedules bunch of input-output operations for these blocks and moves them from free to pending. And then at the end of this written operation, all the blocks from pending are moved to ready. And it is kind of like unclear why this is not IO in, because I would think that, like, while the block is doing IO, it is in IO in, but apparently it is in a pending. Okay. So, yeah. Apparently after we have finished our read, we say, okay, so we no longer need to read the index block, we no longer need to read the data block. We pick our callback and we call the callback. So let's go back to where we started from, which was which I think was actually okay. Actually, I'm lost. So before we do, okay, yeah. So this callback is the callback which is passed to us by the forest, and this is just a generic blip callback. Okay, so we where we your no, that is for already active things, and we are for kicking stuff off. So yeah, we were here. So we said like blip read, and then we pass blip callback. So when we are in this callback, we have already read an index block for table A, for table B, and a bunch of blocks for bunch of data blocks for those tables, but like not all the blocks. Comment in comments that the compaction code is pretty complex and twisty with so much async IO that it is hard to follow for the past few weeks, and I fully agree with that. It's I think this is below our level. I think we could improve it. I think there's like two things here. One is that this is like genuinely complicated code. I think like the problem this is trying to solve is like really complex, because there is like a lot of inherent concurrency where we want to run a bunch of compactions in parallel, and we want each compaction to itself be pipelined, and we don't want to just like independently let all those compactions run, we need to make sure that they are split deterministically across this bar of 32 requests. So that is essential complexity. And this code presently is actually like our first cut at solving that problem. So it works. And it's a good solution, but I think like a good solution in terms of like how the code behaves. But I think in terms of code, we actually could maybe improve it. Well, maybe I'm wrong. I actually started last week, like the first tiny step towards cleaning this up. So hopefully as a result of like our collective suffering on these Twitch sessions, the code will become clearer, and the subsequent generations of connoisseurs of capital wouldn't have to endure this. Or maybe not. Maybe like maybe this is how the best compaction code looks like. Okay. Anyway, let's see what happens in the bleep callback. A lot of happens. Well, actually, no, not that much happens. Like there is like this case for like finishing earlier when we figured out that hey, we actually did finish this compaction, but kind of like we are pretty far from finishing the compaction. So let's go to the advanced pipeline again, and now let's think what is happening here. So on the first iteration, we go in this fitting state. Then we don't go in this for loop because there is no field slots. And we just update field slot +1 here and run this loop. So by the second loop, where we enter here, we get into this code. Okay. And what is our active operation? How do we set active operation? Let's see. So, okay. Somewhat intuitively, which is puzzling, usually things are not as easy to understand, we set our active operation to read. So now, we get to what is advanced pipeline next tick? Like we kind of like don't do here. Oh, okay. Okay. So like, yeah, this is again, this is like some like shady code. The idea here is that we want to, again, in our pipeline, we want the CPU work of merging data and the I/O work of reading data to happen concurrently, right? Like, to make this actually happen, we do need to move merging onto a thread pool. But right now, this is not done. So what this code is like trying to do is just like, just to start CPU work after we submit I/O work. So like still on this single main thread, but after I/O is submitted, and kind of like the comment says that this actually doesn't work, which is, well, we'll believe it. Okay, so the main thing is that like right now we're like only thinking about one slot, but we go like here and here we go and invoke this bleep merge function, which moves us back into compaction. And finally we get to like this real like compaction code. Like everything else was just like stupid setup to like get the data from where it is to where we need it to be. Here, this is the actual compaction work, where we actually go and run this merge algorithm using data from table A, data from table B. and eliminating values which cancel out due to this logical invariant that values on level A always shadow values on level B. Okay. So we have target value blocks, target. Okay, yeah, so target value blocks is this block 5.0. And I think the interested blocks for us are in this ready 5.0. And this is a really convoluted code because this is a var, but this is also a pointer. Like this should be const. I'm pretty sure this should be const. Let's check if this compiles, and probably this doesn't compile because there is a bunch of unrelated changes by me. So let's reset what we have here and try. Okay, now I am lost. Okay, so first kind of like, okay, so this version of code compiles, and now if we change this to const, then hopefully it will also compile because okay, so now it makes sense, because if these were like mutable pointers which were themselves reassigned, I would have died. Okay. Well, maybe not literally, but definitely metaphorically. Okay, so the idea here is that where is okay? Yeah, I would have expected this to be simpler. Okay, yeah. So this is like the core loop of a compaction, where we have values from level A, values from stream of values from level A, stream of values from level B. We compare two values. If this is less than, we like advance one. If this is greater, we advance the other. And if it's equal, we kind of like do this like actual compaction, actual override. So this is like this smallish fragment of code here, like is the actual compaction, like the actual like the reason for the thing where we take two values and we like merge them into one, and we advance both of our indexes. So you see, like source index A advanced here and here, and source index B advanced here and here, and in this case we like advanced both by one. Okay. But there is a whole lot of setup before we go to the actual merge loop. So let's try to peel through this setup and understand what is going on here. Okay, so we have table builder. Table builder is the thing which buffers in progress table in memory while it is written to disk. Actually, table builder, it should be relatively simple. So it tracks the k-mean, k-max for the table, because the meta information about the table includes its minimum and maximum key. Then there is index block and the pointer to the current data blocks. So builder is kind of like a streaming kind of thing. We fill one data block, we write it to disk, then we start writing the next data block. And the initial state is no blocks. Okay, so we are in the no blocks. If target index block ready count, and that's ready. That is that bunch of FIFOs I have. Okay, yeah. This is like This is like my 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 least favorite struct in Tybidal, because like every time I look at this, I'm like what is happening here? Okay, so if okay, so it's like okay, so no idea. Sorry, because really I kind of like don't currently get why we need this here. But well, okay, so normal case, allegedly normal case. We take this. So target index block is, yeah, this is this like FIFO thing again. So this block FIFO, yeah, block FIFO is like that bunch of FIFOs. Okay, so yeah, we allocate one free index block. Zero it out and say, okay, so take a table builder. This is your index block. Then we need to assign similarly the value block. And okay, so this actually repeats. Well, I guess that's the same thing where we can't where we I'm doing as best as I can. That's the same thing where we don't want to do more than half of the work in the same bit. So we kind of like we try to finish this early. Okay, so yeah, we kind of like got both the blocks. Then let's see what is set source level A, set source level B doing. Well, let's start with set source level B, because I think that's going to be simpler, because it only has to deal with the case where things are in memory. So we are okay, yeah. So basically, we want to like figure out what is the actual size of values we need to merge, and store this in the source level B values. Okay, and for some reason back doesn't work. Okay, where we were, how was this function called? It was bleep merge. Yeah, and it was set source B, which is we take the index block for the current table we are currently merging. We take all the values. We slice the values by how many values are in that physical table, and then we slice from the beginning the number of values which we have already processed. So this position kind of like tracks where in the level we are. Okay, now for source level A. So for table immutable case, this is basically the same code as for level B. And yeah, probably like, you know, I kind of like love to joke about object-oriented programming, but probably this is the case where, like, you know, some object-oriented thinking would help to like actually reduce this duplication, because yeah, kind of like we have like this mutable table, they are kind of like the same, but also they're kind of like different. Anyway, okay, for level A. Okay, level A, which is immutable. We call field immutable values. Okay, so yeah, okay, so probably this needs some extra pre-processing here, which is Interesting. Yeah. Okay. So okay. It is so much better when you understand what the code is doing. Okay. So basically, like this is a significant difference between in-memory table and all the other tables. So let us remember how we get our in-memory table. In-memory table is essentially append-only log of all the events which happen, which originally is constructed in arbitrary order. So we just like append stuff, and for example, if there is like insert, then remove, and insert, then remove, then table immutable will have like this insert, remove entries. And originally, the entries in immutable table are sorted by the time of arrival. When we start compaction, we sort table mutable so that the values are sorted by their times, so that the key value pairs are sorted by keys. I kind of like, again, you might object that I kind of like use keys and values interchangeably, but again, for target middle, we aren't really handling key value pairs. Rather, we just handle values, and keys are just parts of a value. So anyway, that means that by the time we get here, our values in table immutable are sorted, but they might contain duplicates. So if you have like insert A, then remove B next to each other, you might actually want to annihilate them. And this is actually like, okay, so kind of, this is, this would be like a very hilarious like comment to place on this function, because that's actually what it is doing. This is like unique utility from Unix, where we take a sorted array and we remove duplicates. So we take our table immutable and then we go and merge them. So so source is our like original table with duplicates. Target is our table without duplicates. And if the key is equal to the next one, then we update the source, but we keep the target the same. So we skip over one value and take the latest one. If they're different, we pick the two of them. And if this is a secondary index, we implement secondary index optimization, for which I think we are going to have a whole separate episode. So let's just ignore this case. Let's assume that our table is not secondary index. Okay, so we did this unique, and then we basically done. Where we were calling this from? We were calling this from set source A. Okay, what is happening here? Okay. We fill immutable values, then we say updated field count. Oh, I think another thing here is that, oh right, so our target buffer might actually be shorter than our what's our source? Source is bar table info a immutable, and target is source a mutable block. Well, yeah, right. So table immutable is like the whole table of values, which is the memory. And compaction operates at the block granularity. So we actually cannot place the entire table immutable in single data block. Table immutable is a table, and block is less than a table. So that's why this fill immutable values actually doesn't do this all the way up, but goes only until we have space in the target. So that's why we have this extra loop here. Well, an extra loop meaning that this thing is going to be called repeatedly, so we kind of like going to incrementally chomp on the values from our immutable table. And yeah, so kind of like we only apparently we only do this is if we actually like have to update our values. So then we kind of like reset something and return either filled or exhausted, which will hopefully actually. And for source level B, do we? Okay, we also return this. Wait, I haven't seen how we handle. Okay. So this is also asynchronous, like the Rust future will like tries to do the work and then might return pendant. So actually, okay. So then let's maybe read this code, which is the same as for level B, more carefully. Okay, yeah. So like this is important. This also has this need read case. So again, if you remember at the beginning, we kind of like we read some blocks from level A and some blocks from level B, but we not necessarily read the entire table. So it might be the case that the data we need to fill the block with is still on disk. So that is also the reason why we might return a need read here, which is kind of like sort of equivalent to Rust future poll pendant. And this is boot merge. And yeah, if kind of like any one of them needs read, we like try to break out of it. Okay, so we are at an hour, and it probably makes to stop here. Again, we kind of like small step every time, but eventually we'll get to it. Eventually we'll cover the entire compaction. So what we have covered today. We finally glimpsed at that actual compaction loop, like at this case, which actually allows us to save data, but we kind of like didn't actually get to it. We are within a spitting distance, but yeah, we still need one more episode to fully catch up. What we covered is the path for how we load the values, which are going to merge in the next episode from disk. And the idea here is pretty simple. So we have compaction. Compaction has a certain pool of blocks, and it just tries to read some amount of blocks, but not more than half of those. Once we finished that reading, we then go from the reading phase of our pipeline to the merge phase of the pipeline, where we will try to run the merge loop, but this merge loop is going to be like a synchronous loop with interruption, because at some point in our like merge work, we will realize that, hey, actually we need to read more data to proceed with our merge, and that will keep our pipeline turning. So thanks a lot for joining. Thanks a lot for frying your brains with me. This isn't it like one of like the most like challenging arcs of our Iron Middle show, and hopefully I will see all of you, and maybe even more than all of you, right here at 5 p.m. UTC on Thursday, live on Twitch next week. And if you didn't make it, then, well, there is also always a recording of the entire series on YouTube, which I think is like 40 or maybe even like 50 episodes already. So we did cover a lot of ground for the past quite a few months. Again, thank you, and see you next week.